Hello everyone and welcome to Microtrac's free webinar measuring electric power generation byproducts. My name is Claudia Gaitan and I will be your moderator today. If you have any questions during the presentation, please type them into the question box in the control panel and we'll be happy to answer your questions at the end of the presentation. A recorded version of this webinar will be available on the website microtrac.com. Your speaker today is Terry Stauffer. Terry works closely with Microtrac as a particle characterization specialist. He has over 40 years of experience in the industry. In today's presentation, we'll go over the pollutants produced in power generation and the abatement processes for these pollutants. We'll also discuss the byproducts produced and how particle characterization can help determine the quality of the products generated. And at the end of the question, we'll be answering any questions. So without further ado, I'll turn it over to Terry.
Thanks, Claudia, and thank all of you for attending. So let's get started. Power generation pollutants include sulfur dioxide, particulates, and coal slag. SO2 gas forms sulfuric acid when it reacts with rain. Fly ash causes smog and water pollution, where it can leach into groundwater and produce acids and other corrosive or poisonous compounds. Coal slag is a gas-like solid recovered from the bottom of the furnace in coal-fired plants and processed and sold rather than disposed of in a landfill where it can leach into groundwater. Pollution abatement processes include wet stack gas scrubbers, which flow stack gas past slurried limestone to produce a solid sulfur compound which ends up as gypsum. Bag houses flow gas through woven bags to collect particulates, and electrostatic precipitators flow gas through a housing of electrodes which attract particulates. SO2 precipitates with limestone to form gypsite, calcium sulfite, which is then further oxidized to gypsum, calcium sulfate, which is sold to wallboard manufacturers at a net profit covering pollution abatement costs. Fly ash is used as fillers for plastics and additives to the clinker or final product of Portland cement. Fly ash also enhances plastics' properties like strength, hardness, and heat resistance, and it increases the long-term strength and lowers the permeability of Portland cement. And coal slag is processed to be used as grit on roofing tile. Particle size and shape characterization for quality of byproducts. Size of particulates of limestone, gypsum, fly ash, and slag must meet the size requirements of the customers who use them for further processing. Limestone must be small enough for adequate surface area for fast enough reaction with SO2 gas emission. Gypsum must meet a narrow size distribution for wallboard manufacture. Fly ash ultrafines must be removed for it to be useful as a filler in plastics. And coal slag needs milling and screening to reduce it to optimum size for shingle coatings. Particle size and shape characterization for quality of byproducts. Multiple sizes and shapes give complete characterization. 28 times as many particle characterization measurements with image analysis compared to a single size with other technologies. This provides much more information about the particles being processed, and the more knowledge one has about their material, the better equipped they are to find solutions to problems. As an example, particle flowability is a very general property of all particulate systems, which affects material flow, packaging, compaction, and separability throughout all process steps. Two shape factors, in addition to size distribution, have a significant effect on flowability: surface roughness and aspect ratio. As each increase, flowability decreases. This has an effect on both the preparation process and the process to convert the particles into a final product. Another general concern in particle processing is the presence of contaminants. Contaminants can be identified, isolated, and quantified by image analysis. Particle characterization techniques, both the well-established laser diffraction, LD technology, and the relatively new dynamic image analysis, DIA technology, are used to characterize particulate systems. Laser diffraction measures the angle and intensity of light scattered by particles from a coherent light source, usually a laser, and an iterative algorithm is used to calculate a size distribution. Dynamic image analysis uses a strobe light to backlight particles flowing through the sensing zone, while a digital camera records a video file of the images of the particles. Knowing the size of the pixels, all the size and shape parameters can be calculated. The video file can be rerun under different standard operating procedures. Particle size and shape for quality of byproducts. Laser diffraction. Here, a particle size distribution are reported by laser diffraction for limestone, fly ash, and gypsum on the left. And all tabular data is given on the right. Particle size is reported by laser diffraction as equivalent spherical diameter, or ESD, usually in log normal volume percent. Particle size and shape for quality of byproducts, dynamic image analysis. A small portion of image analysis data is shown here. The display on the left presents the complete scrollable image file of the particles measured. Hundreds of thousands of particles can often be measured in less than 5 minutes. On the right is the scatter diagram showing positions of all particles relative to two of their size or shape parameters, shown in the red X and the Y graphs. Much more on image analysis data will be detailed later. Particle size and shape technologies here in a combination system. This system provides a combination of laser diffraction and dynamic image analysis. It measures particles in the same sample simultaneously in one measurement. The sample flows from the pump on the left upwards through the DIA and then through the LD unit and back to the pump. The system provides both sets of data and reports as soon as the measurement ends. To quickly review the principles of laser diffraction technology, smaller particles scatter coherent light at wider angles than do larger particles. The scattered light is collected by Fourier lenses in this 3-laser model and is focused on different arrays of diode detectors, which measure the intensity of scatter at all angles from 0 to 165 degrees. The scattered light distribution is then mathematically deconvolved to calculate the particle size distribution. This particular model uses 2 blue lasers and 1 red laser as light sources from different angles. The blue lasers at lower wavelengths than red lasers provide the most accurate fine size information. Laser diffraction size data. This is a comprehensive sample data report from the software for laser diffraction. Clockwise from top left, there's the detailed tabular size distribution, the frequency distribution graph, the standard operating procedure or SOP information, the list of percentile data, and the summary data. all information required on most QC reports. Here's a schematic and photo of the DIA unit. This is a very straightforward measurement technology, but with extremely powerful data analysis after measurement, providing a wide variety of morphological information. Particles flow through the sample cell between a high-speed strobe light on the left and a digital camera on the right. A video file of the particle images is sent to the computer. All the analysis takes place on the recorded images, and the video image file is saved and can be remeasured. This is a set of parameters reported for dynamic image analysis, and rather than go into each in any detail, I'll describe in 4 general terms what they measure. First, of course, is size. We give you 13 different size measurements of each particle in various diameters, lengths, widths, thicknesses, and more. The last 3 columns are shapes of various natures and are generally expressed as ratios of size parameters. Form factors include 11 different parameters that indicate how closely the particle is to being a perfect sphere, or aspect ratios of the particle. Surface roughness parameters are just that. 3 different parameters can indicate the roughness factor of the particle surface. 2 other parameters report the overall light intensity coming through the particle and the curvature of the particle as a function of that light intensity. But don't be overwhelmed by this large number, because no more than a few parameters are needed for any particular application. But there are enough choices here to meet your particular needs. 6 different size or shape distributions can be plotted in the distribution graph here on the left in various formats. 6 plots of historical records can also be shown for comparative purposes. Tabular data for these 6 distributions in the graph are shown on the right. Width and area equivalent diameter, dA, are shown here in cumulative percent finer, and roundness, aspect ratio, and count percent in differential formats. In this display, the full image file can be scrolled through, viewed, sorted on any parameter, exported, and printed. Selecting the search button in the top left allows isolating populations of particles meeting certain parameter limits, and that distribution can be reported. Multiple parameters can be used to isolate a population, and multiple searches can be set up. The image file can be displayed as data in a spreadsheet format and exported. The image file as data. Rows are each particle image measured by ID number. Columns are all the different size and shape parameters for each image in the rows. The image file can be exported directly into a working spreadsheet. The scatter diagram here in blue shows where each particle of this gypsum sample is relative to convexity, or roughness factor, and sphericity on the y-axis. These particles are extremely smooth and fairly spherical. Any size or shape parameter can be selected to be displayed on either axis. Summary data for each parameter selected is listed in the right column. Percentiles, mean, standard deviation, and relative standard deviation. An area of the scatter diagram population can be isolated, as shown inside the green box in the blue particle population. The largest population density in dark blue is chosen here, and the X and Y axis, convexity and sphericity distributions, now correspond to that area selected in the scatter diagram. The numerical lower and upper limits of these parameters can be used to search for this population of particles in the View Particles, Search Particles section. And only that population will then be shown in the image file. See the next slide. A search in View Particles display for that same population of particles isolated in the previous scatter diagram was made here. The image file now contains only those particles searched for, and it reports that the isolated population makes up 38.83% by volume of the sample and 4,900 out of 8,010 particles in that sample. Here in the View Particles display, the particle query window is opened by selecting the Search Particles button, and a search for the group of particles isolated in the scatter diagram is created. Particles with convexity greater than 0.98 and a sphericity greater than 0.8 and less than 0.95 were selected. Selecting the OK button then executes the search and creates the new View Particles display we saw in the previous slide. Any number of searches can be set up for one sample, and any number of parameters can be used in one search. Any searches tried can be set up in the filter function feature to be applied to an SOP, which then runs all searches in the filter automatically when a sample is measured. To summarize, power generation plants need to treat a number of products of combustion to prevent pollution like SO2, particulates, and coal slag. Treatment can be such that saleable byproducts can be made to recover or even make profit over treatment costs. Such products include gypsum for wallboard, fly ash for plastics, fillers, and cement additives, and slag for grit in asphalt shingles. These products need to meet physical specifications for the consumers, which can be measured with laser diffraction or dynamic image analysis technologies for characterizing particles. DIA technology can provide an additional 28 size and shape parameters to fully characterize particles and identify parameters that could be leading to poor quality in the product.
Thanks everyone for joining us today.